picking up where we left off in the first part, we are just after example 9. We're going to talk about the complement of an event. The complement of an event in probability is going to be the set or the group of all outcomes in the sample space that are not in the event. Okay, in other words, these are outcomes that do not satisfy the event. They're the unfavorable outcomes. Okay. For example, if I go back to example 9 here, the complement of the event that I was actually working with, which was the probability of a consonant, would be the probability that I get a vowel, because that's the only other option that I have. Some of them are very cut and dry like that, to where the complement is just the other group of things. Sometimes there's more options and you gotta be a little bit careful with it. There is a way to calculate this. The probability that an event E does not happen, so E is just an event here, so the probability that something does not happen is equal to 1 minus the probability that it does happen, which that should make sense if we think back to that range of outcomes that we can have for probability. Okay, 1 is certain. That's what all of our probabilities have to add up to be. And so if some group of them make up some probability, the other half of, or the other group of that 1, that total probability has to be the other part. Okay, and so we can use that to our advantage. Let's look at number 10 here. There are 35 students in a study hall. The table below shows the number of students who are taking each foreign language. What is the probability that a randomly selected student is not studying a foreign language? Well, I know I have 35 people, and I know how many are in each one, so let's figure out how many people are not. So, if we add these together here, there are 21 total. Okay? Well, that means that 21 out of 35 people are in a foreign language. I'm abbreviate it FL. Okay? Which means that not a foreign language is going to simply be 1 minus that. Or I can just say, well, I'm going to take 21 people away from the 35, which means I have 14 out of the 35 people that are taking a foreign language. Okay? I can divide that out. It gives me 0.4. which is the same thing as 40%. Okay, again, I'm giving all 3 answers. The other thing I do want to point out as well, I'm not reducing fractions. This is one of the only times in math where we don't want you to reduce, because this 35 has meaning. This is the total number of people. So I don't want to lose that 35. That means stuff. So we're going to keep that. We won't reduce any of our fractions. Let's talk about number 11. Number 11 is going to bring us back a little bit to where we started. I have 2 integers, so 2 numbers from 1 to 10 that are randomly selected. The same number may be chosen twice. What is the probability that both numbers are less than 9? So I want to think of this almost like the password, where you have 2 places. Okay? Well, my total number for each of these is going to be how many total choices I have. Well, my total here, line this up. I would have 10 numbers for the first one and 10 numbers for the second, because I'm picking 2 integers. I'm picking 1 through 10. There's 10 options there, and I could also pick 1 through 10 for the second number. If I multiply those, just like our fundamental counting principle tells us, I have 100 options total. Okay, let's talk about when both are less than 9. Okay, well, that takes away some of my options with each choice. Okay, well, if I'm saying it's less than 9, then I can pick 1 through 8. So I have 8 choices that I could pick that would make this less than 9. So I would say that the first option could be out of 8. And I'm allowed to repeat numbers. I say I can use the same thing twice, so I would also have 8 for the second one. And multiply that out, and I get 64 options that are less, where both numbers are less than 9. So now I need to set it up as a probability. Well, you have 64 favorable outcomes out of a total of 100. Hopefully that makes sense of the way I set that up, that this was my total divided by my number of times it can actually happen. Okay, if I divide that out, I get 0.64. or 64%. Okay, I'm actually not going to tell you at all how to round on these, because if you're questioning how to round, leave it as a fraction. Fractions you do not have to round. So I'm almost actually pushing you to use those unreduced fractions because they have that little bit of meaning there that makes more sense. Okay, getting down to the last page here, this is where we're going to switch from the theoretical stuff and we're going to move into experimental. Okay, so experimental is where we carry out a probability situation to see the outcomes. Okay. When we do this, we get a couple new words we need to talk about as well. We have a trial, which is each repetition of an experiment, or each kind of time that I try whatever I'm trying to do. The experimental probability then, okay, is still a probability, so it's still going to be a ratio, it's still dividing, but here it's the number of times the event occurs to the number of trials. So in other words, it's how many times it worked divided by how many times I tried it. Okay. Let me give you a very kind of simplistic example of experimental probability. Let's say I have a coin. I don't know if the coin is fair. I don't know if it's always going to be 50-50. So the way I decide to test it is I flip it 100 times. Okay. So I'm going to take this coin. I'm going to flip it once. I see what the result is, and I write it down. I record what happened. Then I move to the next one. Okay? Each time I flip the coin is what we refer to as the trial. The experiment is this idea of flipping the coin 100 times. The experimental probability then I could figure out based on how many times I got heads or how many times I got tails. That could then help me decide whether that coin is fair or not. Okay? It might not tell me exactly. Like if I get, say, 51 heads and 49 tails, does that mean that the coin is not fair? Probably not. It's still pretty close to 50-50. But if I end up getting 5 tails and 95 heads, that's probably an indication that it is skewed in some way. So experimental probabilities are often used to estimate theoretical probabilities and to make predictions. But the problem with experimental is they're based on experiments. They can change. Okay. Just a quick note here based on what's happening right now. The models that we talk about in the news are based on experimental probabilities. We don't know everything about our virus that we have going on, and so they have to make certain guesses and make basically some trials happen to see what would happen if we say that this is what it is. Okay, and that's the way those models work out. Okay, so let's get to some simple stuff though that we can understand here. Example 12, we have the table shows the result of a spinner experiment. Find the indicated experimental probability. So we're spinning a spinner. I have the numbers 1, 2, 3, 4. Occurrences means that that's the number of times that it happened. So spinning a 4 happened 14 times. So that's going to go on top. But I also need to know how many times did I actually spin the spinner. So I need to add all of these together. If you do that, I get a total here of 50. So I'm going to put 14 over 50, which is the same thing as 0.28 or 28%. Again, you can give me any of those answers. And what about spinning a number that's greater than 2? Well, greater than 2 is either the 3 or the 4, so I need to count both of those. So 19 and 14 gives me a total of 33 that worked out of the total of 50. 33 divided by 50 is 0.66, or 66%. Okay. What about the probability of spinning not a 3? Well, the easiest way to do that is take your total and just simply subtract the 19. Because I have all the information, you could also just simply add the 6, the 14, and the 11. Either way, I'm going to end up with 31 out of my total of 50, which is 0.62, or 62%. Okay. Final one, what's the probability of spinning a 5? Okay, now this is important here. I have no idea what the spinner actually looks like. So the idea that they're asking me about 5 seems like an outrageous question because I don't have 5 listed. But that could just mean that 5 never happened. Okay, so I have to say here that the probability is 0, but that doesn't mean that 5 is not on that spinner. Okay, and that's really important. That's going to be highlighted more in the next example as well. Okay, experimental probabilities are strictly experimental. They do not exactly match theoretical probabilities. Okay, I also don't know if these are even spinners. I don't know if it's completely split into quarters or if I do have 5 on there somewhere into fifths. I don't know, and so that's why this experiment and this data that I have is really important. Let's talk about 13. So we have a table is shown with the results of choosing one card from a deck, recording the suit, and then replacing it back. So I have a deck of cards. I don't know if it's a full deck. I'm just pulling out cards. I don't know if I have all of them there or not. I want the probability of choosing a diamond. Well, I have 9 diamonds, so I know I'm going to get 9 over my total. If I add my total up here, there are 26 cards. So I would say 9 out of 26, which is going to equal 0.3462, or 34.62%. Okay, again, if I were you, stick to your fraction. Part B, choose a card that is not a club. Get rid of the 7. Take 7 away from 26, leaves you with 19. So we have 19 out of 26. It's equal to 0.7308, or 73.08%. Okay. Again, just going back to the fact that this is experimental, not theoretical, I have to use this data that I have. Okay. In a standard deck of cards, the probability of choosing a diamond should be a quarter. It should be 25% because I have 4 suits. Clearly in this one, I'm getting that more often. Now, that could be just because I haven't done it enough times, the probabilities haven't evened out yet. Or it could mean I have more diamonds than I should, or less of the other cards than I should. And so those are where we can start to make those decisions of are things fair or not, just based on these experiments. Okay, we'll be doing more with experimental probability eventually. Maybe this year, maybe not. Depends on how far we can get. But experimental probabilities are definitely applicable in the time that we are in right now. If you want to talk about that more or have any questions, let me know, and we can go through those.